Hello. Yeah, good evening. Sorry no for changing the platform tonight because gigamit sa din sa office ang Zoom no sa Masteral Defense sa Graduate Studies po. So we are using the Google Meet na lang tonight no for the presentation. So nana ba si Engineer Bandules?
Yes, sir. Good evening po.
Yeah, Engineer Bandules. How about si Engineer Doriente?
Sir, present, sir. Present, sir.
Presentation for the interest of time, Engineer Bandules. No, if you are ready, please start the presentation. To be followed by Engineer Doliente, Orabao, Espinosa, and Manoy later. So, reminder, no, when presenting, please turn on your cam, no, mga presenters. Thank you.
Ay, hello, sir. Good evening. Should I start na po?
Yes, proceed, Engineer Bandules.
Oh, okay. Thank you, sir. Sorry, kaya medyo putol-putol sa akong end. Mag-share screen sa ako. Okay, but visible po ba sa tanan? Kasi mag-assume po na visible.
Proceed, Engineer Bandules.
The structural dynamics case study. So this case study, case study focuses on the 2015 Gorka, Nepal earthquake and its heritage masonry structures in Kathmandu Valley. The main purpose of this presentation is to understand how traditional heritage structures responded to earthquake loading, why certain damage patterns occurred, and how structural dynamics concepts such as seismic demand, damage patterns, seismic demand, stiffness degradation, natural frequency change, stress concentration, and out-of-plane instability can help explain the observed damage. In this study, heritage buildings are treated not only as cultural monuments but also as structural systems subjected to dynamic forces. This is important because when a heritage structure is damaged, the loss is not only architectural or cultural. It's not only architectural or cultural. It also reflects a structural safety problem that requires engineering interpretation. So for today's presentation, I will discuss the rationale and background of the study, including the earthquake event, the tectonic setting of Nepal, and heritage context of Kathmandu Valley. Second, I will present the objectives of the case study. Third, I will give an executive brief which provides an overview of the main focus and findings. Fourth, I will discuss the highlighted details particularly the procedure and methodology used in this case study. After that, I will proceed to the results, including the seismic event characteristics, general heritage damage, typical damage mechanism, structural system vulnerabilities, Jagannath Temple case study results, in situ testing, ambient vibration results, and finite element modeling interpretation. Then I will discuss the engineering interpretation and lessons, followed by the conclusion and references. So the Gorka Temple earthquake occurred along the Himalayan arc between magnitude of 7.8. It was followed by numerous aftershocks, including a major 7.3 aftershock on May 12, 2015. These repeated seismic events caused widespread damage across central Nepal, including Kathmandu Valley. From a tectonic perspective, Nepal lies along the active Himalayan seismic plate. The Indian plate is converging with the Eurasian plate. This convergence is accommodated along the main Himalayan thrust, which is capable of producing large earthquakes. So Goda et al. Explained that the 2015 earthquake occurred along the Himalayan arc between the Indian and Eurasian plates, with rupture propagating from west to east and from deeper to shallower parts of the fault plain. This is important in structural dynamics because the earthquake demand is not only controlled by the distance, local soil condition, and frequency content and duration of shaking. So the Kathmandu Valley contains major cultural heritage structures, including temples, palace complexes, towers, shrines, and monuments. Many of these structures are part of the UNESCO World Heritage Property. Their damage represents both this slide is that the 2015 Gorka earthquake created a strong need to evaluate the seismic response of heritage structures, especially because many of them were constructed before modern seismic codes and were not designed for earthquake resistance. So this slide shows the earthquake caused extensive damage to heritage areas, particularly in Kathmandu Valley. The before and after condition of Patan Durbar Square illustrates the heritage monuments were directly exposed to seismic demand. These were not ordinary buildings. These structures carried, again, architectural, religious, historical, and social significance. So from an engineering point of view, the damage shows that the cultural monuments are also structural systems. They have mass, stiffness, load paths, connections, materials, and foundations. So when subjected to earthquake motion, they develop inertial forces, deformation, cracks, and possible collapse mechanisms. So the important idea here is that heritage damage should not be interpreted only visually. A collapsed roof, a cracked wall, or a separated corner is not simply an architectural defect. These are signs of deeper structural behavior such as weak lateral resistance, poor wall connection, insufficient confinement, and failure of the load transfer system. Therefore, the study connects cultural loss with structural vulnerability. So many heritage structures in Kathmandu Valley are traditional masonry timber systems. They are commonly composed of brick or stone masonry, mud mortar or lime mortar, timber posts, timber beams, timber wall plates, ring ties, and heavy clay tile roofs. These materials and systems are historically valuable, but they also create engineering challenges under earthquake loading. Because masonry perform well in compression, but it is weak in tension and shear. During an earthquake, lateral shaking produces tensile and shear stresses in the masonry walls. If these stresses exceeds the wall capacity, cracking may occur because unreinforced masonry has limited ductility. The failure can be brittle and sudden. Another issue is the heavy roof mass. In structural dynamics, earthquake force is related to mass and acceleration, di ba? So the heavier the structure, the larger the inertial force generated during ground shaking. Heavy clay tile roofs increases the seismic demand on walls, especially when the connection between roof timber members and masonry walls are weak. So these structures are also often lack modern seismic features such as continuous load paths, ductile detailing, reliable wall-to-floor wall-to-roof connections, adequate confinement, and strong diaphragm action. Without these features, the earthquake force may not be properly transferred through the structure. Instead, force may concentrate in vulnerable areas, leading to cracking, separation, or collapse. So, the engineering problem is that these heritage masonry structures are massive, brittle, irregular, and connection dependent, making them highly vulnerable to seismic loading. So, under earthquake loading, the weakness of heritage masonry structures may lead to several failure mechanisms. These include diagonal tension cracking, which occurs when shear demand exceeds the tensile capacity of masonry, out of plane wall deformation, where walls move perpendicular to their plane due to inadequate anchorage or confinement. The laminar outer white separates from the inner wall core. Corner wall separation, often caused by lack of confinement, roof collapse, especially where heavy roof system are poorly connected, and finally partial or total collapse. So Shrestha et al. Identified this typical damage pattern in Nepalese heritage structures after the 2015 Gorkha earthquake. They explained that such damage can trigger sudden or brittle collapse, especially when the internal construction, geometry, materials, and mechanical properties are not properly understood. So this leads to the main question of the study. Why did the heritage masonry structure fail under seismic loading? So the answer is not simply that the earthquake was strong. The more complete answer is that the damage occurred because of the interaction between earthquake demand and pre-existing structural vulnerability. So the general aim of this case study is to evaluate the seismic performance and damage behavior of heritage masonry structures in Kathmandu Valley during the 2015 Gorkha, Nepal earthquake, with emphasis on structural dynamics, damage mechanism, and engineering interpretation of the vulnerability. The first objective is to describe the seismotectonic background and ground motion characteristic of the 2015 Gorkha, Nepal earthquake. This includes understanding the earthquake magnitude, rupture mechanism, aftershock sequence, and the role of Kathmandu Valley's local site conditions. The second objective is to identify and classify the major damage patterns observed in heritage masonry structures. This includes damage such as diagonal cracking, wall separation, delamination, roof collapse, and total or partial collapse. So the third objective is to examine the structural characteristics of Nepalese heritage buildings that influence their seismic performance. This includes their masonry timber system, heavy roofs, timber connection, and traditional wall composition. The fourth objective is to analyze the structural vulnerabilities that contributed to earthquake damage, such as weak masonry behavior, poor bonding, discontinuous load paths, timber deterioration, and inadequate confinement. The fifth objective is to evaluate Jagannath Temple as the principal technical case study. Jagannath Temple was selected because it was investigating using visual assessment, in situ testing, ambient vibration testing, and finite element modeling. The sixth objective is to interpret the observed damage using structural dynamics concept, including stiffness degradation, natural frequency change, stress concentration, and out of plane instability. The seventh objective is to discuss engineering lessons and conservation sensitive strengthening measures for heritage masonry structures. This means that the study does not only identify failure, it also consider how heritage structure can be assessed and strengthened without destroying their cultural and architectural value. So this case study evaluates the seismic performance of heritage masonry structures in Kathmandu Valley during 2015 Gorkha, Nepal earthquake. The main finding is that damage resulted from interaction of earthquake demand and pre-existing structural vulnerability. Traditional heritage structures in Nepal commonly use masonry timber system. This system may have heavy roof mass, weak masonry, limited ductility, and discontinuous load paths. Because of this characteristic, they are vulnerable to seismic effects such as diagonal cracking, wall delamination, out-of-plane deformation, roof collapse, and partial or total collapse. So the case study also focuses on the Jagannath Temple, which provides one of the strongest technical basis for analysis because its damage was assessed through visual inspection inspection, in situ material testing, ambient vibration investigation, and finite element modeling. The before and after images of the Jagannath temple show that this structure had already experienced a major earthquake events in the past, including the 1934 Nepal Bihar earthquake and the 2015 Gorka earthquake. This historical exposure is important because previous damage, repair works, aging, and material degradation may influence present seismic performance. So, proceeding to the highlighted details, the published heritage structure assessment, visual documentation, field testing results, and ambient vibration findings and finite element modeling results. The first step was the review of the seismotectonic and ground motion background. This helped establish the earthquake demand during the 2015 event. The second step was the review of published earthquake damage survey data, especially from God et al. And Shrestha et al. The third step was the identification of common heritage structure damage pattern, principal technical case study. The fifth step was the review of visual damage assessment and in situ material testing. Sixth was the review of ambient vibration and dynamics concept. And the final step was the review of conservation sensitive strength and measures. So for the methodological approach, this slide shown summarizes the methodology as a document-based case study supported by structural engineering interpretation. The study synthesizes several sources of evidence. These include earthquake demand, damage observation, material testing, dynamic assessment, numerical modeling, and engineering interpretation. The principal technical case is Jagannath Temple, based mainly on the study of assessment, ambient vibration testing, in situ test using the rebound hammer, pendulum hammer, and in-place push testing, as well as the finite element modeling. It is also important to clarify that this study does not claim original field testing or original numerical modeling. Instead, it interprets published results from a structural dynamics perspective. So the objective is to connect the published evidence with engineering concepts. The methodology allows the study to explain the heritage masonry damage using the relationship between the earthquake demand, material conditions, stiffness loss, stress exceedance, and structural vulnerability. The sequence at the bottom of the slide shows that the logic of the study is earthquake demand leads to damage observation. Damage observation is supported by material testing. Material testing informs dynamic assessment, and dynamic assessment is supported by numerical modeling, and all of these are interpreted through the structural engineering principles. So, proceeding to the results. So, the first result focuses on the seismic event characteristics and earthquake demand. The 2015 Gorka, Nepal earthquake occurred on April 25, 2015, with a moment magnitude of 7.8. It occurred along the Himalayan arc and the main Himalayan thrust. The main shock was followed by several aftershock, include the 7.3 aftershock on May 12, 2015. From the structural dynamics perspective, the main shock aftershock sequence is very important. The main shock may cause initial cracking, stiffness degradation, connection damage, and displacement of vulnerable structural elements. After that, aftershocks may impose additional dynamic demand on the structure that are already weakened. This means that the structure after the main shock is not the same structure dynamically. Its stiffness, strength, damping, load path, and boundary condition may already have changed. Because of that, even if an aftershock is smaller than the main shock, it may still cause significant additional damage. So Goda et al. Also discussed the earthquake rupture propagated along a large fault area, and that the KAT and P station provided valuable strong motion data near Kathmandu's historical district. Although the recorded peak ground acceleration in Kathmandu was not necessarily the highest possible hazard level, vulnerable old masonry buildings still experienced severe damage. Therefore, the result shows that the earthquake damage was not controlled by seismic demand alone. It was controlled by the interaction between seismic demand and structural vulnerability. The second result shows that the heritage damage was not isolated or superficial. It affected multiple monuments and multiple heritage structures. This indicates that the building typology, material weakness, HDTE totally collapsed, 97 partially collapsed, and 515 were partially damaged. In Kathmandu Valley alone, 447 monuments were affected and 83 collapsed completely. Impact on heritage structure, the damage was not isolated or superficial. It affected multiple monuments and multiple heritage zones. Thus, the slide also shows that the building tower, damage to surrounding buildings, collapse of old multi-story masonry buildings, and collapse of a four-story masonry building. So the important finding is that severe damage was concentrated in old masonry and heritage structures. This indicates that the building typology, material weakness, age deterioration, and lack of seismic detailing were major contributors. So the key message here is that the severe heritage damage was not caused by ground shaking alone. It was caused by, again, the interaction between the seismic demand and the structural vulnerability. The third result focuses on typical damage mechanisms. Shrestha et al. Observed several common failure mechanisms in heritage masonry structures after the 2015 Gorka earthquake. This includes separation of corner walls, collapse of top roof systems, lamination of outer masonry wall layers, diagonal tension shear cracking, out of plane wall deformation, and partial or total collapse. Each of these mechanisms has a structural explanation. So corner wall separation occurs when the connection between the intersecting walls is weak or when there is inadequate confinement. Under lateral shaking, the corners may crack and separate because they cannot contain the masonry anymore. Tensile strength of masonry. Out of plain wall deformation occurs when the connection between the
Okay, so I think intermittent signal in the Banduri, so we will wait for a moment or for a while for him, for her to finish the presentation. Audible ko Engineer Dea ba? So we'll wait for maybe 1 to 2 minutes para mabalik sa Engineer Banduri.
Hello, good evening everyone. Nabalik na ba? Sorry kay wala ko
Yes, ma'am.
kabantay na wala. Hello?
Yes, ma'am, naa na, ma'am.
Ay, okay. Thank you kayo sa feedback, sir. So, mag-continue na lang ko an the fourth result examines the structural system of Nepalese heritage temples. Traditional tiered temples are typically masonry timbers. Thank you. So, they use brick or stone, masonry walls, mud mortar or lime mortar, timber posts, timber beams, wall plates, ring ties, heavy clay tile roofing, and sometimes multi-layer masonry wall composition. So Shrestha et al. Explains that the tiered temples are generally square in plan and may have two or three roof tiers. Their walls are often composite, consisting of inner brick masonry, outer facing bricks, and core filled with brick fragments and mud mortar. So timber elements are very important in the structure. Timbering ties and wall plates can provide additional shear resistance and improve the connection of walls. They may also provide some flexibility and energy absorption during earthquakes. However, the beneficial effect of timber depends on its condition and continuity. If timber elements are decayed, missing, poorly connected, or discontinuous, the temple loses a critical part of its seismic resistance. So the key structural issue is that the seismic performance depends on connection quality, wall banding, material condition, and load path continuity. If one of these is weak, the structure may not behave as integrated system during shaking. So this slide continues the discussion of structural vulnerabilities. The major vulnerability factors include weak masonry in tension and shear poor banding between masonry layers, the lamination of the outer wall width, heavy roof mass, discontinuous load path, decayed or disconnected timber elements, and previous repairs or incompatible work. So masonry is strong in compression but weak in tension and shear. Under earthquake loading, tensile and shear stresses develop in walls. If the wall capacity is low, cracks form. So poor bonding between masonry layers is also critical. A wall may look thick and strong from the outside, but its internal layers are not well bonded. It may act as a single structural unit. It may not act as a single structural unit. This can lead to delamination and reduction of effective wall thickness. So, heavy clay tile roofs increase inertial forces. Since earthquake force is related to mass, heavy roofs increase seismic demand on the walls and connection. These continuous load paths are also dangerous. If the load from the roof or upper walls does not transfer directly to the foundation through continuous structural elements, eccentric forces and stress concentrations may occur. The slide summarizes this as material weakness plus connection failure plus irregular load transfer leads to observed damage. So the key message is that the temple system can resist earthquake forces only when masonry, timber, roof, and wall elements act together as one connected structural system. So moving on to the fifth result. The fifth result focuses on the Jagannath Temple. Jagannath Temple is located in Kathmandu Darbar Square and was selected as principal technical case because it had documented damage, in situ testing, ambient vibration, investigation, and numerical modeling. It is a traditional tiered heritage masonry timber structure. It had previously been damaged during the 1934 Nepal Bihar and uh, earthquake and was reconstructed from the plinth level in 1935. After the 2015 Gorka earthquake, the most significant damage was concentrated in the upper masonry walls. The observed damage include diagonal tension, shear cracks, out of plane wall deformation, wall inclination, and upper wall damage. Shrestha et al. Reported that all four top story walls experienced out of plane deformation and the maximum top story was wall deflection was 45 millimeter. This is important because out of plane deformation is a serious sign of instability in masonry structures. It indicates that the wall may not have sufficient anchorage, confinement, or lateral support. The interpretation is that the upper portion of the temple was more vulnerable to lateral movement during earthquake, because the lower portion of the temple was closely connected to the analysis. This new testing means that the tests were performed directly on the existing heritage structure. This is important because the material properties of old masonry structure may be different from assumed laboratory values. Over time, the materials may be affected by aging, previous repairs, moisture exposure, workmanship, and earthquake damage. According to Chesta et al., three in situ tests were used in the investigation. First, the rebound hammer test was used to check the surface hardness of the masonry wall. Second, the pendulum hammer test was used to evaluate the strength of the mortar. Third, the in-place push test was used to assess the bed joint shear strength of the masonry. These tests help describe the actual condition of the wall materials and joints, which is important in understanding the temple's earthquake vulnerability. The table on the right shows the result of the pendulum hammer test for the lime mortar. The average rebound number was 36 with a standard deviation of 8. The average rebound number represents the strength of the masonry wall. The pendulum hammer number represents the strength of the mortar. The lime mortar had an estimated compressive strength of 3.7 MPa, and the mortar quality was classified as normal C. Um, the rebound number was interpreted using the applicable calibration or empirical relationship for the pendulum hammer test. It is also important to note that that even though the mortar was classified as normal, this does not automatically mean that the temple was structurally safe during the earthquake. The seismic performance of the temple still dependent on other factors such as wall banding, timber connection, roof mass, load path continuity, and existing cracks and out of plane wall stability. Compared with a normal building, the lime mortar strength of 3.7 MPa is much lower than typical structural concrete, which may commonly have strengths such as 21 MPa or 28 MPa, depending on the design. But this comparison should be made carefully because the test here is for lime mortar, not concrete. A modern building also has reinforced concrete beams, column slabs, and seismic detailing, while Jagannath Temple relied mainly on traditional masonry, lime mortar, timber elements, and heavy roof system. So the key takeaway from this slide is that the actual in situ material properties must be considered in assessing heritage masonry structures. Mortar strength directly affects wall shear resistance. Cracking behavior and overall seismic vulnerability, while earthquake damage must always be interpreted together with the entire structural system. For the second part of Result 6, the study presents the condition assessment findings of Jagannath Temple after the 2015 Gorkha, Nepal earthquake. Baseline in Jagannath Temple was constant out of observed. This is important because the upper portion of the temple was more vulnerable to lateral movement during earthquake shaking. The figure also shows that the temple had different masonry wall composition. This matter because if the wall materials are not uniform, the stiffness, strength, and seismic response may also vary from one part of the structure to another. In heritage buildings, some areas may have original materials while other parts may have been repaired or replaced over time. Because of this, the structure may not respond evenly during an earthquake. Another important finding is the inclination measurement of the top floor wall. This supports the need for detailed in situ testing and structural assessment because some weaknesses cannot be fully evaluated by visual inspection alone. A wall may still be standing, but it has already tilted or deformed. It may have reduced stability and could become more vulnerable during aftershock. The in-place push test also showed an average bed joint shear stress of 0.109 MPa for the lime mortar masonry wall. This stress is significantly higher than the recommended stress of 0.001 MPa for the lime mortar masonry wall. evaluation in understanding the actual earthquake resistance of the wall. However, the test results were only preliminary. They still showed that the NC2 strength of the existing structure may differ from laboratory-based material values. This means we should not rely only on measurements. So the implication is that actual material condition must considered must be considered in heritage structural assessment, especially for old structure exposed to aging, deterioration, previous earthquake damage, and restoration interventions. Trust the observed damage in Jagannath Temple with its actual wall condition and seismic vulnerability. This slide presents one of the most important findings of the case study because it shows how the actual post-earthquake condition of Jagannath Temple was evaluated using ambient vibration testing and finite element modeling. First, Shrestha et al. Developed an initial finite element model of Jagannath Temple using SAP 2000, a finite structural model where the structure is divided into smaller parts so its behavior can be analyzed. In their model, the masonry walls were represented using solid elements, while the timber members were modeled as natural frequency and understand its structural behavior under seismic effects. So the initial SAP 2000 model produced a fundamental frequency of 4.5 Hertz. However, the actual was measured using ambient vibration of microtremor testing. The measured frequency was only 2.6. So microtremor testing records a small natural vibrations of structure caused by environmental sources such as wind, ground movement, traffic, or nearby activity. So this difference is very important because in structural engineering, stiffness means the ability of structure to resist deformation or movement when a load is applied. A stiffer structure usually has a higher natural frequency, while a less stiff or damaged structure has a lower natural frequency. Since the measured frequency of the actual temple was much lower than the initial model frequency, this indicated that the real structure was less stiff than the model originally assumed. In other words, the initial model made the temple appear stiffer than it actually was. Because of this, the researchers modified the finite element model by reducing the stiffness values to better represent the actual damage condition of the temple. This modification was done to calibrate the model with a measured microtremor result. The reduced stiffness represented the effects of cracks, material degradation, weakened conditions, and earthquake damage. After stiffness reduction, the model frequency became 2.96 Hz, which was closer to the measured microtremor frequency of 2.6. This confirmed that the stiffness degradation was an important factor in the temple's actual dynamic behavior. So, the key takeaway is that the Jagannath temple may still have been standing, but dynamically it had already weakened. The lower measured frequency served as evidence of stiffness degradation, showing that earthquake damage changed the temple's structural behavior. Also, to clarify, I did not create a new SAP 2000 model for this case study. I used the SAP 2000 result from Shrestha et al., a secondary technical evidence, and interpreted them from the structural dynamics perspective. So continuing from the previous slide, after the researchers identified the actual condition of the Jagannath temple through in situ testing and ambient vibration testing, they further evaluated the structure using finite modeling. The previous slide showed that the measured microtremor frequency of the actual temple was 2.6, which was lower than the initial analytical frequency. So this indicated that um, the temple had already experienced stiffness degradation due to cracks, material deterioration, and earthquake damage. So, to understand this behavior more clearly, Shasta et al. Developed a three-dimensional finite element model of Jagannath Temple using SAP 2000. The purpose of this model was to analyze how the temple behaved structurally, identify areas where stress concentrated, and compare the numerical results with the actual damage observed in the temple. In the model, the masonry walls were represented using solid elements because walls behave as three-dimensional components with height, length, and thickness. On the other hand, the timber members were modeled as the frame elements because timber posts, beams, and roofs members behave like linear structural members. So the table shows the mechanical properties used in the model. These include density, compressive strength, shear strength, modulus of elasticity, Poisson's ratio, shear modulus, and shear wave velocity. These values were taken from Shrestha et al. And were based on Parajulis material property data. They served as input values in SAP 2000, so the model could represent the behavior of masonry and timber elements. So, for example, the masonry wall had a density of 1,768 kilogram per meter cube, compressive strength of 1.82 Newton per millimeter squared, shear strength of 0.15 Newton millimeter squared, and modulus elasticity of 509 per millimeter squared. These values help represent the mass strength and stiffness of the masonry wall. The timber had a density of 8,000 kilogram per meter cube and much higher modulus of 12,500 Newton per millimeter squared, which means it was modeled as stiffer than the masonry wall. This modeling approach is important because the visual inspection and material testing can tell the condition of the structure, but finite modeling helps explain why the damage occurs. It allows the researcher to see whether concentrations in the model with the actual damaged areas of the temple. So this slide continues the previous finding by showing that the lower measured frequency and observed wall damage were not isolated results. They were supported by numerical modeling, which provided a structural basis for explaining the damage. The key message is that the finite element model helped connect the observed damage with the actual structural behavior of Jagannath Temple. It showed that the cracks and deformation were not random but were related to stress concentration, weak masonry capacity, and reduced stiffness after the earthquake. So this slide shows the stress distribution results from the numerical model. The left figure shows the direct normal stress, while the right figure shows the direct shear stress under earthquake loading in the x direction. The colors in the diagram represents the different levels of stress based on the legend beside each model. So what is important is to identify which zones have stress values that approach or exceeds the allowable masonry capacity. The left diagram, which shows direct normal stress, helps identify areas where tension and compression developed in the masonry walls. This is important because masonry is generally weak in tension. If tensile stress becomes too high, the wall may develop cracking. The right diagram shows direct shear stress. This is also important because the earthquake forces push the structure sideways, creating shear demand in the walls. If the shear stress exceeds the masonry capacity, the wall may experience diagonal cracking, sliding separation, or out of plane deformation. Based on the numerical analysis, Shrestha et al. Found that tensile and shear stresses in the upper masonry walls exceeded permissible limits. What makes this result important is that the stress concentration occurred in the same areas where actual damage was observed in the temple. This explains the observed diagonal tension, shear cracking, out of plane wall deformation, and upper wall distress. The cracks were not surface defects or visual damage. They were structural evidence that the seismic demand exceeded the masonry capacity. So this slide explains the structural dynamics interpretation of the finite element modeling results and how timber confinement improved the structural response of Jagannath Temple. First, the slide compares the initial first mode shape and modified first mode shape. The initial finite model produced a natural frequency of 4. Considering the actual damage condition of the temple, the modified model produced a lower frequency of 2.96 Hz. This reduction frequency is important because stiffness degradation in structure. When a structure cracks or deteriorates, its stiffness decreases. When stiffness decreases, the natural frequency also decreases. Therefore, the lower modified frequency shows that cracking, material degradation, and earthquake damage change the dynamic behavior of the temple. The next important point is the role of timber confinement. Timber confinement refers to the use of timber elements such as timber bands or internal timber framing to help hold the masonry walls together. In heritage masonry structure, timber elements can improve wall connection, reduce separation, and provide additional resistance against lateral earthquake forces. The slide shows that after adding timber elements, the stress demand in the masonry wall was reduced. This means that means the timber helped distribute the focus more effectively and reduce stress concentration in vulnerable masonry areas. This is why timber bands are considered conservation sensitive strengthening measure. They improve the seismic behavior of the structure while still respecting the traditional masonry timber construction system. Instead of replacing the heritage structure with modern materials, timber confinement strengthens the original system in a compatible way. So, um, the finite element modeling connected three important ideas: observe damage, dynamic behavior, and strengthening strategy. The modeling showed that stiffness reduction changed the temple's dynamic response while timber confinement improved its structural performance. In simple terms, the temple became dynamically weaker because of cracking and material degradation, but timber confinement helped reduce stress and improve the structure's ability to resist earthquake forces. The ninth result focuses on the timber band strengthening. The Jagannath Temple case study showed that the horizontal and vertical timber bands are effective strengthening measures for heritage masonry structure. Additional timber elements within the inner masonry wall help reduce induced stress in the structure. Timber confinement improved resistance against shear forces, out of plane deformation, and localized stress concentration. This method is conservation sensitive because timber bands are compatible with three traditional Nepalese masonry timber system. They do not completely replace the original structure with modern materials. Instead, they reinforce the original structural logic of the heritage building. So timber bands improve the integrity of the structure and they help walls act together, reduce separation, increase resistance to out-of-plane movement, and improve load transfer during shaking. So timber band strengthening can reduce the seismic vulnerability by improving wall confinement, reducing stress concentration, and increasing resistance to shear and out-of-plane deformation while preserving the traditional structural identity of the heritage temple. Next, this slide provides the overall engineering interpretation of the result. The main finding is that the damage of Kathmandu Valley heritage masonry structure was caused by the combined effect of the seismic demand and pre-existing structural vulnerability. The key contributing vulnerabilities include weak masonry materials, poor bonding between wall layers, and heavy roof mass, discontinuous load paths, weaker timber connection, and material deterioration and aging. Stiffness
Uh,
degradation.
Engineer Sandhu. Hello.
Yes, sir.
Please wrap up your presentation.
Okay, sir. Sorry, sir. I'll proceed to ano lang, sir, conclusion. Okay, so the first conclusion is that 2015 Gorkha Nepal earthquake was a significant event of evaluating the response of the heritage masonry structure. The 7.8 mean shock together with the aftershock sequence imposed repeated dynamic demand on the Kathmandu Valley. The second conclusion is that the damage was widespread and varied. It was not limited to total collapse. Many structures experienced diagonal tension, cracking, wall delamination, out-of-plane deformation, corner wall separation, roof collapse, partial collapse, and localized failure. The third conclusion is that the structural characteristics strongly influence seismic performance. Nepalese heritage buildings are traditional masonry timber system composed of brick or stone masonry, mud or lime mortar, timber posts, wall plates, string ties, wooden floor systems, and heavy roof elements. When these components are properly connected, they can provide some seismic resistance, but when the load path is discontinuous, our connections are weak, the structure becomes highly vulnerable to lateral shaking. So the fourth conclusion is that the main structural vulnerabilities included weak masonry behavior, poor bonding between wall layers, inadequate confinement, reduced structural integrity, decayed or disconnected timber elements, heavy roof mass, material deterioration, and incompatibility restoration works. Together, these factors reduce the ability of the structure to resist tensile and shear stress. The fifth conclusion is that the Jagannath Temple provided the strongest technical case for explaining the heritage masonry damage. It experienced diagonal tension, shear cracks, and out of plane deformation in the upper masonry walls. The assessment combined visual damage observation, in situ testing, and ambient vibration investigation and finite element modeling. The sixth conclusion is that the structural dynamics concept helped explain the damage. The difference between analytical frequency and measured frequency indicated stiffness degradation due to cracking and material deterioration. Finite element analysis showed tensile and shear stress exceedance in damaged zones. This means that the cracks and deformation were not simply visible defects, they were physical evidence that seismic demand exceeded the masonry capacity. The seventh conclusion is that the timber band strengthening can be a promising conservation sensitive intervention. Horizontal and vertical timber bands reduce stress, demand, and improved resistance against shear forces and out of plane deformation. This type of strengthening is appropriate because it reinforces the traditional masonry timber system while preserving architectural character and material compatibility. The eighth conclusion is that the heritage structure should be treated as dynamic structure systems, not only as a cultural monuments. Their earthquake performance depends on mass, stiffness, natural frequencies, material strength, wall composition, connection, quality, load path, continuity, and energy dissipation. Future assessment should include visual documentation, in situ material testing, ambient vibration analysis, numerical modeling, regular maintenance and conservation, sensitive strengthening. The ninth and final conclusion is that severe heritage damage resulted from the interaction between seismic demand and pre-existing structural vulnerability. The 2015 Gorka, Nepal earthquake demonstrated how structural dynamics concepts can explain observed damage through masonry cracking, stiffness, reduction stress, exceedance, and out of plane instability. Overall, seismic resilience of heritage structures depends on the integrated assessment, compatible strengthening, and preservation of traditional structural character. So these are my references. Thank you all for listening.
Okay, so thank you for your presentation, Engineer Bandoli. So, for the interest of time, we will proceed to the next presenter, no, si Engineer Doliente. Engineer Doliente.
Good evening, sir. Share screen. So good evening, everyone. Good evening, Doc. So this evening, I will be presenting an enhanced FEMA-based seismic vulnerability assessment of reinforced concrete buildings with structural irregularities. So this is a case study of buildings affected by the Izmit earthquake. So the outline is the first is the rationale or the background. Sorry, sir, wala di ko na on-cam. So again, the outline of the case study includes the rationale or the background. Second, the objectives, the executive brief or the summary or the overview of the project. Next is the highlighted details, which includes procedures and methods. Next is the results, the discussion of results, the conclusion, and the references. So first we have the rationale or the background. So in Turkey, many of the heavily populated and industrialized cities are on or near the North Anatolian Fault Line or the NAF. So the region is one of the most important earthquakes prone areas in Turkey. So the 7.4 magnitude Kocaeli or the also known as the Izmit earthquake occurred at 3:01 a.m. local time on August 17, 1999, on the east-west trending north strand of the North Anatolian Fault Zone, or the NAFZ, about 100 kilometer southeast of Istanbul, Turkey. So the approximately 125-kilometer long fault um, rupture and high damage area follows or is close to the south shore of Izmit Bay. So, and the extension of that line to the east and has predominantly 2.2 meter right lateral displacement from Adapazari in the east to, to Yalova in the west. So we have here the figure 1. As you can see, this is the epicenter. Then, mao ni ang katong North Anatolian Fault Zone nga nag-acquire og 2.2 meter right lateral displacement. So the 1999 Izmit earthquake caused widespread destruction of reinforced concrete buildings across urban areas in Turkey, exposing major weaknesses in seismic design and construction practices at the time. So many of the collapsed and heavily damaged structures were not only affected by ground shaking intensity but also by poor structural configurations. So a key observation from post-earthquake investigations was that building failures were strongly associated with structural irregularities, particularly the soft start conditions at ground floors, as it is used for parking or commercial spaces. We have the plan irregularities causing torsional response, then the vertical irregularities that which cause a disruption of load transfer, then the weak story formations leading to concentrated load failure, and lastly, the short column effects producing brittle shear failures. So these irregularities significantly reduce the ability of structures to resist lateral earthquake forces, leading to partial or a total collapse damage. So this case study expands the conventional Federal Emergency Management Agency, or the FEMA rapid visual screening methodology, by incorporating additional structural engineering analysis intended to improve seismic vulnerability evaluation of reinforced concrete buildings affected by the said earthquake. So while traditional FEMA studies primarily focus on the rapid identification of vulnerable buildings, the enhanced studies integrate structural irregularity or the severity assessment, the interaction effect analysis, the collapse mechanism evaluation, and lastly is the FEMA reliability validation based on the post-earthquake documentation or the assessment. So a structural irregularity severity index was developed to rank the relative severity of each structural deficiency based on observed earthquake damage and structural behavior. So the study further compared the FEMA seismic scores with the actual earthquake damage to determine the reliability of FEMA-based rapid visual screening in predicting structural vulnerability and collapse potential. So based on the findings, an enhanced FEMA-based assessment framework was proposed to improve seismic vulnerability evaluation and retrofit prioritization of reinforced concrete buildings. So we have here the objectives. First is the general objective, which is to develop an enhanced FEMA-based seismic vulnerability assessment framework for reinforced concrete buildings affected by the Izmit earthquake through structural irregularity analysis and collapse mechanism evaluation. The specific objectives also includes the identifying the structural irregularities present in the selected buildings. Second, to apply the FEMA rapid visual screening method in assessing seismic vulnerability. Third is to evaluate the severity of structural irregularities and their effect on collapse behavior. Fourth, to analyze the interaction effects of multiple irregularities during earthquake loading. Fifth is to investigate the collapse mechanisms observed during the Izmit earthquake. Six, to validate the reliability of FEMA seismic scores using actual earthquake damage. And 7 is to propose an enhanced FEMA-based framework for seismic vulnerability assessment and retrofit prioritization. So next, we have the executive brief. So the study focuses on 3 representative reinforced concrete buildings that sustained severe structural damage during the Izmit earthquake. The buildings were evaluated using FEMA RVS procedures to identify major structural deficiencies, including soft story irregularity, plan irregularity, vertical irregularity, weak story mechanisms, and short column effects. So these irregularities were analyzed according to their influence on seismic instability, lateral load resistance reduction, and the structural collapse behavior. So to enhance the conventional FEMA methodology, the study developed a structural irregularity severity index, which evaluates the relative severity and collapse contribution of each structural irregularity. The study also examined the interaction effects of multiple irregularities to determine how combined deficiencies amplify seismic vulnerability and collapse susceptibility, since um, ang structure kay wala siya nag-acquire og isa lang ka structure irregularity. So through this approach, the research provides a more realistic representation of earthquake-induced structural behavior compared to the traditional rapid visual screening assessments using FEMA. So in addition to the vulnerability classification, the study investigated the actual collapse mechanisms observed during the Izmit earthquake, including the pancake collapse, brittle column shear failure, excessive interstory drift, torsional deformation, and progressive structural instability. So post-earthquake reconnaissance observations and documented damage conditions were utilized to establish direct relationships between structural irregularities and collapse behavior. The research further evaluated the reliability and predictive capability of FEMA rapid visual screening by correlating computed seismic vulnerability scores with actual earthquake damage experienced by the selected buildings. So the findings demonstrated that buildings with lower FEMA scores and multiple interacting irregularities exhibited significantly greater collapse potential and structural damage. So this validates the effectiveness of the FEMA-based rapid visual screening for preliminary seismic assessment. So we have the highlighted details. So the study utilized a descriptive analytical case study approach integrating the Federal Emergency Management Agency or the FEMA rapid visual screening methodology with enhanced structural engineering analysis. So there are 3 reinforced concrete buildings affected by the Izmit earthquake, selected as representative samples based on the presence of structural irregularities, observable collapse behavior, and availability of post-earthquake damage documentation. So the methodology began with building identification and structural classification, followed by the identification of major structural irregularities such as soft story conditions, weak story mechanisms, torsional irregularities, vertical irregularities, and short column effects. So the FEMA structural score modifiers were then applied to compute the final seismic vulnerability scores of each building. So, kato, the study introduced structural irregularity severity index. Then, gamiton ni siya to evaluate the relative severity and collapse contribution of each irregularity. So, additional analysis included interaction effect assessment to evaluate the combined influence of multiple irregularities, collapse mechanism interpretation based on observed structural failures, and the FEMA reliability validation through comparison of computed seismic scores with actual earthquake damage. So this methodology provided a more comprehensive seismic vulnerability assessment by integrating RVS with structural behavior analysis and collapse interpretation. So step 1 is the kato selection of building samples. So this study selected I mean the buildings were selected based on the presence of um, structural irregularities, the observable collapse behavior, the availability of post-earthquake data, and the relevance to reinforced concrete building configurations. And then for building ID, we have B1, nga naay structural type of RC residential building, and its damage condition is totally collapsed. For building 2, reinforced concrete mixed-use building acquiring a severe damage condition. For B3, we have a reinforced concrete apartment building acquiring a partial collapse damage condition. So mo ni siya ang sa building 1, building 2, and then building 3. So step 2 is the identification of structural irregularities. So the identified irregularities included a soft story irregularity, the weak story condition, torsional irregularity, vertical irregularity, and lastly, the short column effect. So for building 1, the identified structural irregularities present are the soft story and weak story irregularity, weak story condition. For building 2, we have a soft story irregularity and the torsional irregularity. For building 3, we have a vertical irregularity and the short column effect. So step 3, we have the FEMA rapid visual screening assessment. So the procedure involved a structural classification, application of FEMA score modifiers, computation of final seismic score, and the vulnerability classification. So for structural irregularity of soft story, we have a modifier value of negative 0.8, vertical irregularity of negative 0.6, weak story irregularity of negative 0.5, torsional irregularity of negative 0.4, and short column effect of negative 0.4. So the basic structural score, or BS, depends on structural type, seismic design level, and expected seismic performance. So for reinforced concrete buildings used in this study, we have the reinforced concrete moment frame C1 with a 1.7 basic structural score. So more na siyang gigamit sa kanina study. So for the FEMA score range, if the final seismic score S is less than 0.3, it will acquire a very high vulnerability level, and its recommended action is immediate detailed evaluation. So when final seismic score is greater than or equal 0.3 but less than 0.7, it will acquire a high vulnerability level with a structural investigation recommended action. For final seismic score of greater than or equal to 0.7 with but less than 2.0. So its vulnerability level is moderate vulnerability, and its recommended action is for further assessment. So for final seismic score of greater than or equal to 2.0, mag-acquire siya og low vulnerability level, and iyang recommended action is acceptable preliminary condition. So step 4 is the computation of FEMA seismic score. So the final seismic score of each building was computed using the FEMA equation. So the final seismic score S is equal to the basic structural score BS plus the summation of structural modifiers nga katong na ay mga structural irregularities present. So we have here an example calculation for building 1. So B1, since RC man katong moment frame is iyang basic structural score is 1.7. Then naa siya soft story irregularity, which corresponds to a score modifier of negative 0.8. and a weak story modifier of negative 0.5. So the final FEMA score, or the S, is equal to the summation of katong all scores, which resulted to 0.4. So building 1 acquiring a zero point 0.4 FEMA score. So iyang vulnerability classification is very high. For building 2 is zero point 0.5 with high vulnerability. For building 3, 1.0 with moderate vulnerability. So step 5 is the structural irregularity severity index evaluation. So severity levels were assigned based on structural instability, collapse influence, drift concentration, and reduction in lateral resistance. So for soft story irregularity, its severity weight is 5 with very high severity level. Vertical irregularity with 4 severity weight with high severity level. Same sila sa weak story condition, acquiring a 4 severity weight with high severity level, and the torsional irregularity and short column effect acquired a 3 severity weight with moderate severity level. So step 6, we have the interaction effect analysis. So the study evaluated how multiple structural irregularities interact during seismic loading. So the analysis focused on the discontinuous load transfer, the stiffness imbalance, the stress concentration, and the amplified structural instability. So for the discontinuous load transfer, meaning its vertical elements kaya wala siya nag-align. For stiffness imbalance, it deforms unevenly under external loads, which is the earthquake, and it lacks a uniform distribution of stiffness. For the stress concentration, this occurs when irregularities disrupts the flow of the applied forces, and the amplified structural instability refers to the structure's ability to handle loads. So for the combination of irregularities, we have here the soft story and the weak story, which acquires a pancake collapse, the soft story and the torsional irregularity with rational instability, and the vertical irregularity and short column effect having a localized brittle failure. So for step 7 is the collapse mechanism analysis. So the collapse mechanisms evaluated and includes a pancake collapse, torsional instability, brittle column failure, and progressive collapse. So ang building 1 kay pancake collapse, building 2 is torsional instability, and building 3 is partial collapse due to vertical irregularity. So the FEMA step 8 is a FEMA reliability validation. So the reliability of the FEMA RVS was validated by comparing FEMA seismic scores with actual earthquake damage. So building 1 with 0.4 FEMA score, iyang actual damage is total collapse since ang katong sa previous result is high vulnerability man siya. Acceptable yang reliability result. So step 9 is the development of the enhanced FEMA-based framework. So this final step involved the development of an enhanced FEMA-based seismic vulnerability assessment framework integrating of FEMA rapid visual screening, the structural irregularity severity index, the interaction effect analysis, the collapse mechanism interpretation, and the FEMA reliability validation. So we have the results. So the overview of results. The results of the study demonstrated that Structural irregularities significantly influence the seismic vulnerability, instability, and collapse behavior of reinforced concrete buildings affected by the Izmit earthquake through the enhanced application of the Federal Emergency Management Agency or FEMA Rapid Visual Screening methodology. The study identified the relationship between structural deficiencies, seismic vulnerability, interaction effects, and the actual earthquake damage. So the three representative buildings identified as B1, B2, and B3 were analyzed using the said procedure integrated with structural irregularity severity index evaluation. Then interaction effect analysis, collapse mechanism interpretation, and FEMA reliability validation, and the results revealed that buildings possessing multiple structural irregularities experience significantly greater structural instability and collapse susceptibility during the strong earthquake excitation. So next is the result. So for first is the FEMA rapid visual screening result. So for building 1, again, it is a reinforced concrete residential building with kung ano ni siya ang summary na ni siya sa result. So ang present structural irregularities is the soft story and weak story with a 0.4 FEMA score and has very high vulnerability. Ay under siya sa very high vulnerability classification. So for building 2, it is a reinforced concrete mixed use building with soft story and torsional irregularity and FEMA score is 0.5 and the vulnerability classification is high vulnerability. So for building 3, the RC apartment building, ang present is ang vertical irregularity and short column effect. Then na siya 1.0 FEMA score which corresponds to a moderate vulnerability. So key findings. So B1 obtained the lowest FEMA score due to the combined presence of soft story and weak story conditions. For building 2, also exhibited high vulnerability because of soft story behavior combined with torsional irregularity. Building 3 obtained a relatively higher seismic score but still sustained significant structural damage due to vertical irregularity and short column effects. So structural irregularity severity results. This was developed to determine the relative severity and collapse contribution. So for soft story irregularity, naa siya 5 with observed structural effect of severe drift, concentration, and first story instability with very high level. Ang vertical irregularity with 4, discontinuous load transfer and high severity level. Weak story condition of 4 severity weight with reduced lateral resistance and high severity level. And the torsional and irregularity and short column effect with 3 severity weight with observed structural effect of rotational deformation, then with moderate severity level, and brittle shear cracking with moderate severity level. So the key findings is that soft story irregularity produced the highest structural severity among all identified deficiencies. So weak story and vertical irregularity significantly reduced the stability and stiffness continuity of the buildings. And the torsional irregularity amplified rotational response during seismic loading, and the short column effect caused brittle localized structural failure. For the structural irregularity severity index, so B1 with the presence of multiple irregularities, its total severity score is 9 and classified as very severe. For building 2, we have the soft story and torsional irregularity with a score of 8 and is classified severe. And building 3, the presence of vertical irregularity and short column effect with a 7 total severity score and severity classification of moderate to severe. So key findings is that building 1 obtained the highest severity score due to severe first story instability. Building 2 demonstrated amplified structural instability caused by torsional response, and building 3 experienced localized collapse due to vertical discontinuity and short column behavior. So for the interactive effect analysis results, for B1, the presence of these two irregularities, nag-acquire siya og pancake collapse for building 2 with soft story and torsional irregularity with severe rotational instability, and building 3 with vertical irregularity and short column effect, and its observed structural consequence is localized brittle failure. So key findings is that buildings with multiple irregularities experience more severe damage than those with isolated deficiencies. Then the interaction between soft story and weak story conditions produced progressive collapse behavior, and the combined torsional and soft story effects generated severe structural distortion. For the collapse mechanism results, B1, its collapse mechanism is pancake collapse, and the observed structural behavior is progressive first story failure. For building 2, the torsional instability with uneven lateral deformation. Building 3 with acquiring a partial collapse with brittle localized failure. So key findings is that building 1 exhibited classic soft story pancake collapse behavior. Building 2 experienced severe torsional deformation and column cracking. Building 3 Building 3 has sustained localized structural failure due to discontinuous stiffness distribution. And for FEMA reliability validation results, we have B1 of 0.4, very high, and its actual damage is total.
Please wrap up your presentation.
Okay, sir, mag-proceed na lang po sa conclusion po, sir. So the overview is that the study concludes that structural irregularities play a dominant role in determining the seismic vulnerability, damage, severity, and collapse behavior of the reinforced concrete buildings affected by the earthquake using the enhanced FEMA rapid visual screening framework. Then the study successfully evaluated the relationship between structural deficiencies, seismic scores, interaction effects, and observed earthquake damage. So for the key conclusion on FEMA RVS is that building 1 and 2 recorded very high to high vulnerability classifications. Building 3 showed moderate vulnerability but still experienced damage. And to conclude, the FEMA RVS is effective in identifying highly vulnerable reinforced concrete buildings based on observable structural conditions. So the second key conclusion is the structural irregularities. So most critical findings is ang soft story irregularity with most severe condition, the weak story condition of reduced lateral resistance, the vertical irregularity with load transfer disruption, the torsional irregularity of rotational instability, brittle failure. Conclusion is that soft story behavior is the most dangerous structural condition leading to catastrophic collapse. Then the key conclusion on interaction effects, soft story plus weak story, mag-acquire siya og pancake collapse or total collapse, soft story and torsion with severe distortion, and vertical plus short column with localized failure. So multiple irregularities are more dangerous together than individually present sa structure. So the key conclusion on collapse mechanism. So the pancake collapse, mo ni siya ang soft story failure. Then the building 2 with torsional instability, and building 3 with localized brittle collapse. So each collapse type is directly linked to specific structural irregularities. So fifth key conclusion on FEMA reliability. So low FEMA scores will acquire a severe collapse damage, and moderate scores will acquire a partial collapse damage. So conclusion, the FEMA RVS is reliable for preliminary seismic vulnerability assessment. So for final conclusion, the enhanced framework. So the enhanced FEMA-based framework improves the traditional seismic assessment by adding the structural irregularity severity index, the interaction effect evaluation, the collapse mechanism interpretation, and the reliability validation. So the enhanced framework provides a more accurate, comprehensive, and engineering-oriented seismic vulnerability assessment tool than conventional FEMA RVS alone. So the study concludes that structural irregularities and their interaction effects are the primary drivers of seismic collapse in reinforced concrete buildings, and that the enhanced FEMA-based methodology offers a more complete and practical approach for seismic vulnerability evaluation and for retrofit prioritization. So here are my references, and that's all for this evening.
Thank you, Engineer Ira, for the presentation. Question is, you mentioned about vulnerability. So, what are the parameters of the vulnerability?
So ang parameter sa vulnerability sir kay ang gigamit nila is katulad yung sa post-earthquake nga result gani sir.
In terms of what? Ang vulnerability. What are the parameters?
Ang gigamit nila sir is katong present ra sa ang presence of kuan sir structural irregularities.
Like, unsa nga parameters? Structural irregularity lang. Only a single parameter.
Yes sir, since nag-focus gid siya sa assessment gani sir sa um, assessment sa katong post-earthquake na nga mga kuan sir, collapse nga buildings.
So, how is the story of FEMA about the structural irregularity? How it was being done?
Sir, sorry sir. Sir.
How it was being done, the scoring of the structural irregularity?
Ang katong
Using,
scoring sir, ang katong sa using score modifier sir.
how do they score the structural irregularity?
Ay kani siya sir, kaning FEMA score ay I mean akato. Kani sir. Kaning modifier value sir. So kani siya sir kay gi-evaluate ni sa katong sa FEMA gani sir nga nato siya table na ang soft story irregularity na siya like equivalent value na gid siya sir nga negative 0.8 sir. Ug kani pong sa uban nga irregularity sir.
Can you see the table of FEMA?
Sir, sorry sir.
Can you show the table of FEMA? You have mentioned about the table. Can you show us?
Ay, okay sir. Wala ra ba siya nako na-include sa akong presentation sir, pero naka-search ko adto sir na siya sa level 2 nga kuan sir. Katong assessment table nila sir.
Yeah, kindly prepare that one later no, after the
Sige sir. Yes
after
sir.
the class.
Yes. Sir.
So, thank you so much. So let's proceed to Engineer Urabaw.
Okay sir, thank you.
Good evening, everyone. Good evening, Doc. Let me just share my screen. Okay. Is my presentation visible? Okay. Thank you, sir. So, good evening once again. So, my presentation is about Taipei 101 tuned mass damper. So, um, the outline of my presentation are the following. We have first the rationale or background, the objectives, executive brief, highlighted details, results, discussion of results, conclusion, and references. So for the rationale or background, we have here Taipei 101 is one of the best example of structural dynamics engineering in modern high-rise building. So it is located near the Pacific Ring of Fire, and also the tower is exposed to strong earthquakes and typhoons. So to reduce vibration and improve structural performance, engineers installed 660-ton tuned mass damper, which can you see here sa atuang photo, no? Demonstrating the practical application of vibration control technology. Also, the tower has a 101 story and is approximately 508-meter tall, and it is located in a high seismic region and is frequently exposed to extreme wind loadings from typhoons. So, in the next slide natin siyang i-discuss further, but from this slide, we have here the wind niya nga ano 'no, wind speed in meters per second. We have the minimum wind speed and the maximum gust wind speed kaning green. This is from a typhoon Sodelor, which is siya ang nagpalihok sa tuang TMD 'no for approximately 1 meters no kasway. And also we can see here that for the second photo is ang seismicity sa atoang sa Taiwan, specifically sa Taiwan. So Taipei 101 is located in Taiwan and a region with high seismic due to its proximity to active tectonic plate boundaries along the Pacific Ring of Fire. So the area is frequently experiences earthquakes generated by plate interaction and fault activity. So because of this seismic environment, high-rise structures such as the Taipei 101 must be designed to resist significant lateral forces and structural vibration. So the seismic map shown on the right illustrates the large number of earthquake events occurring throughout Taiwan, emphasizing the highly active tectonic environment surrounding Taipei 101 from the 1900s to 2012. So Taiwan is located along the Pacific Ring of Fire and one of the most seismically active region in the world. So it is also situated near the convergent boundary between the Eurasian plate, kining sa ibabaw, and uh, the Philippine Sea Plate, diri no, Sea Plate, where continuous plate interaction generates frequent seismic activity and tectonic movement. So as we can see here no, natay duha ka plate nga mura siya og ah, napatungan sa atong Taiwan no. And also, wind environment. So Taipei 101 was designed to resist extreme typhoon-induced wind forces through aerodynamic plan shaping. So tall buildings are vulnerable to vortex shedding where alternating wind vortices create crosswind excitation and lateral vibration. So wind tunnel studies showed that the square corners generated large wind-induced responses. So to reduce structural vibration, engineers adapted to design it through a double notch or sawtooth corner modification as we can see here sa ato ang Taipei 101 na building. So this geometric modification significantly reduced lateral response and aerodynamic performance. And also, uh, the construction of the Taipei 101 is also considered the historical dynamic hazard. So Taipei 101 was designed in response to Taiwan's frequent earthquakes and typhoon activity. So they have considered no kaning mga strong earthquakes like the 1999 Chichi earthquake emphasized the importance of seismic resilience, while strong typhoon wind made dynamic loading a major design considerations. As a result, vibration control systems such as the tune mass damper became essential for structural stability and occupant comfort. So because of this event, no, seismic resilience became a major consideration in the structural design of the Taipei 101. So in addition, aside po datong aning earthquake na po tayo katong mga strong wind nga iyahang ma-experience po ani nga region. So due to combined seismic wind hazard, advanced vibration control such as kaning TMD were incorporated sa pagdesign sa building. To improve comfort for the occupant and enhance overall structural performance during extreme loading events. So tune mass dampers or tune mass damper or TMD is passive vibration control. So passive siya meaning dili siya active no. Device used to reduce structural motion in tall buildings. So it operates by moving opposite to the building's oscillation, counteracting dynamic forces caused by wind and earthquakes. So by reducing acceleration and lateral displacement, the TMD improves structural stability and occupant comfort in super tall structures such as the Taipei 101. So the objectives of this case study are to identify the structural dynamic problems encountered by super tall buildings such as the Taipei 101, to explain the working principles and components of the Chun mass damper system installed in the Taipei 101, to determine how the TMD reduces structural displacement and acceleration through vibration control mechanisms, and to present engineering computations related to natural frequency, damping ratio, and mass ratio of the TMD system. And also to evaluate the effectiveness of the TMD system based on published engineering studies and monitoring data, and to discuss the significance of structural motion control system in modern high-rise building designs. So the Taipei 101 is a landmark example of, for the executive brief, the Taipei 101 is the landmark example of structural dynamics and vibration control in super tall buildings. It is located in Taiwan, no, along the Pacific Ring of Fire, and the tower is exposed to strong earthquakes and typhoon winds, requiring advanced structural engineering system. So Taipei 101 was the tallest building in the world from 2004 to 2010 until the Khalifa surpassed it. And also it is completed no atong 2004, and it stands approximately 508-meter tall with 101 floors and a floor area of about 4 412,500 square meter. So it was designed to maintain stability, safety, and occupant comfort under extreme environmental loading. So the construction of the Taipei 101 presented major engineering challenges, no, due to seismic activity, typhoon loading, and the dynamic behavior of tall structures. So increased height results in greater lateral movement and structural vibration, making vibration control critical. So to address these challenges, the tower utilized a mega frame structure system, na siya outrigger trusses, no, and deep foundations, and a 660-ton tune bus damper, which the study was focused on. Installed near the top of the building, the TMD helps reduce sway and improve structural performance during earthquake and strong winds. So as we can see here, no, naa siya sa ako na discuss later ang iyang approximate location sa ato ang tune mass damper. uh, Highlighted details, structural dynamics, and the need for tune mass dampers. So modern super tall buildings are highly susceptible to dynamic excitation caused by the wind, earthquakes, and human-induced vibrations. So unlike conventional low-rise structure, tall buildings possesses lower natural frequencies and longer vibration period, no, since ubo man iyang frequency, so ang iyang period is longer, making them more sensitive to resonance effects and lateral motion. So according to the dynamics of structures, structural motion becomes critical when external excitation frequencies approach the natural frequency of the structure. So it's just like kanang sa example no, kanang mag-swing bitaw kanang sa swing, if ma-tune nimo ang frequency to the natural frequency is murag mo taas ang iyahang ano no, ang mahimo siyang critical kay mo kusog ang imong pagsway. So Taipei 101 was constructed in a region exposed to severe typhoons and high seismic activity. Studies by Chen and Lin showed that the tower experiences measurable dynamic responses during both typhoon and earthquake events. So to control excessive vibration and improve occupant comfort, engineers incorporated the world's largest tube mass damper suspended near the upper floors of the tower. So mo no, the Taipei 101 tune mass damper consists of 660 metric ton suspended steel sphere positioned between the levels 87 and 92. So 5 levels of the building. So according to Dennis Poon, the damper mass represents approximately 0.24% of the total building mass and functions as a giant pendulum system. So the steel sphere is suspended using high-strength cables and connected to hydraulic viscous dampers. So during strong winds or seismic excitation, the building begins to sway while the suspended mass moves in the opposite direction. So this counter motion dissipates kinetic energy and significantly reduces structural acceleration. So the TMD was tuned to the building's fundamental first mode frequency of approximately 0.15 to 0.17 hertz, corresponding to the primary lateral sway motion of the tower. So kaning 0.15 is siya approximately ang iyahang period is nasa mga 6.8 seconds. No? So this tuning allows the damper to resonate with the dominant vibration mode of the structure, enabling the suspended mass to move out of phase with the building's motion and effectively reduce displacement and occupant discomfort during typhoon winds and seismic events. So diri day located ang ato ang tune mass damper, no. Its materials are solid steel and built from 41 circular steel plates, each approximately 125 mm squared. So gipatong-patong siya nga ano, no, nga circular steel plates with a total mass of 660 metric tons. And its cable, 8 high strength steel cables supports the TMD. So each cable is approximately 42-meter long and 9 centimeter in width. So made of thousands of steel strands for strength and flexibility. So it has a diameter of 5.5 meters and material sa TMD sphere. Uh, there are 8 hydraulic dampers. No? Sorry, this is a damper. No? 8 hydraulic dampers installed around the base. So these dampers control the movement of the TMD and dissipate energy. So the dampers are connected between the TMD support structure and the building frame. Um, and we fundamental principles of tune mass damper. So ang iyang fundamental gid nga principle, no, a tune mass damper is a passive vibration control device designed to reduce structural oscillation by transferring vibration energy away from the main structure into a secondary oscillating mass. So the TMD operates by tuning its natural frequency close to the natural frequency of the structure. When resonance occurs, the damper oscillates out of phase of the building, generating counteracting internal forces that reduces structural displacement and acceleration. So kato, no, ang ato ang passive control nga system is kaning ato ang tune mass damper. So it's passive, so limited lang po ang iyahang frequency nga counteract, specifically ang iyaharag yung close to the building's natural frequency. So according to Sung and Dargosh, passive control systems such as TMD are highly effective because they dissipate energy without requiring external power system. So mao din ni ang iyahang diagram, no. We have here the main mass or the mass sa building and ang mass sa ato ang damper. So this diagram illustrates the fundamental principle of the tune mass damper, no. Uh, the larger mass represents the primary structure, the smaller mass represents the tune mass damper through a secondary spring. So the external harmonic force ani represents dynamic excitation such as wind or earthquake loading acting on the structure. Aside from the actual full-scale monitoring, no, which will be discussed later, a study was conducted to analyze the response of the Taipei 101 using computer software modeling. So, nagtry sila og analyze sa building. They used duha ka method, the 2 degree of freedom dynamic modeling, which katong kaganina pod nga diagram na atay main mass and the mass of the tune mass damper. Also, they have also used 3 degree of freedom dynamic modeling na atay mass nga natay first mass main mass katong from ground to the 87th floor ang lower part sa atong building. Second is the tune mass damper itself and third is the upper floors katong from 95th to the 101st nga floor. So ako lang po i-discuss, no, these equations represents the 3 degree of freedom dynamic system with coupled masses, springs and damping. So each equation describes the motion of individual mass while accounting its interaction with adjacent masses through stiffness and damping forces. So next, wind-induced structural vibration. So wind loading is one of the governing design considerations for super tall buildings. According to Asan Karim and Kwok, tall flexible structures are highly vulnerable to vortex shedding and aerodynamic excitation. So the Taipei 101 experiences strong typhoon winds that can exceed 60 meters per second. And full-scale monitoring studies reveal that wind excitation can generate substantial lateral acceleration and occupant discomfort if not properly controlled. So the TMD significantly reduces the peak acceleration response and limited excessive sway motion during extreme wind events. So as we can see here sa ato ang GIF, no, GIF, kani siya nga sway was induced during that typhoon sa Pilipinas is the Super Typhoon Hana in 2015. Um, kato no, 1 meter, approximately ang iyang sway is nasa 1 meter. So it is the largest, it was the largest sway nga na-record sa atong June mass damper. So earthquake response and energy dissipation. So Taiwan is located katulagi within a highly seismic region influenced by the interaction of tectonic plates. So earthquake-induced vibrations can produce substantial lateral displacement, interstory drift, and dynamic amplification in super tall structures. Simulation results showed that when seismic excitation was applied to the lower structural masses of the Taipei 101, the TMD absorbed a significant portion of the vibration energy. So after the earthquake input ceased, the damper continued oscillating while gradually dissipating the residual energy through viscous damping mechanism. So the studies by Chen confirmed that TMD improved the post-earthquake dynamic stability of the structure. So we have come to the results now, the results of the dynamic response analysis. So the analytical simulation demonstrated that the tune mass damper significantly reduced the dynamic response under multiple loading conditions. So ang pinakaduol nga iyahang pinakaduol sa actual building is the 3 degree of freedom no katong lower level atong TMD and the upper level of the building. So other under impulse loading, the main structural mass experience an immediate oscillatory response after excitation. So, however, the building rapidly returned toward equilibrium while the absorber continued oscillating for a longer duration of absorber meaning katong TMD. So this behavior confirmed that the TMD successfully transferred vibrational energy sway from the primary result that dissipated it through damping mechanism. So the study also observed no kato ganin ang 3 degree of freedom produce more realistic vibration than the second degree of freedom. Mao din ang iyahang results no, iyahang graph. So as we can see it during the simulation of the blast excitation near the 88th floor, which corresponds to the location of the tune mass damper, the lower floor experienced minimal impact and exhibited very small vibration amplitudes. So the results also showed that the TMD and the upper floors had nearly the same vibration amplitude because the excitation was directly applied near the absorber and the upper structural zone. So as we can see here no, ang iyahang magnitude, ang iyahang measure no is nasa mas ubos ang lower nga scale. As we can see here nga ang iyahang na naka unit siya by 10 to the power of -8 and ang upper floor is 10 ang lower floor is 10 to the power of -10. So parehas lang siya graph but ang iyahang ano lang unit no scale. So also the results under wind and harmonic excitation. So the simulations under harmonic and wind-like excitation revealed that the tune mass damper remained highly effective during sustained oscillatory loading. So during the resonance condition, the absorber oscillated out of phase while with the building reducing the amplitude of the structural vibration. So the results showed that as long as the force function remained active, the structure continued vibrating with controlled amplitude. So once the excitation stopped, the building quickly stabilized while the TMD gradually dissipated the remaining energy. And results of the earthquake response analysis. So aside from the wind nga ilahang i-impulse direct sa 88th floor, nag-conduct pod og nag-try pod sila og earthquake simulations. So the damper during earthquake simulations, the lower structural mass of Taipei 101 was subjected to approximate seismic excitation. So the numerical results showed that the structure experienced significant oscillatory motion during the active loading period. So however, once the seismic excitation ended, the tune mass damper continued oscillating and gradually dissipated the residual energy. So mao din ang iyahang result. As we can see from the first 288 floor, napod siya ang naa siya ano no, vibration response. So the 3 degree of freedom earthquake response analysis showed that the tuned mass damper effectively reduced the vibration response of Taipei 101 earthquake excitation. So the upper floors experienced larger vibration amplitudes compared to the lower floors due to the greater lateral displacement at higher elevations. The absorber continued oscillating while the amplitudes of the structural responses gradually decreased, indicating the TMD was absorbing and dissipating vibration energy from the system. Uh, Effects of damping ratio, last na siya nga result, no? The parametric analysis showed that the damping ratio has a major influence on the effectiveness of the tune mass damper. So when absorber dump was reduced to zero, gitry nila nga walay damping coefficient, no? Oscillations continued and extended duration with minimal reduction in amplitude. This demonstrated that the TMD mass alone is insufficient without adequate energy dissipation capability, meaning katong iyahang mga viscous damper sa ubos. No? So as damping coefficient increases, the setting time of the structure decreases substantially. And they reported that increased damping by 3 times, approximately 30 seconds to about 20 seconds ang iyahang decay period. No? So mao dayon ni siya ang iyahang result. So responses of the first 288 with zero absorbing damping, meaning wala tay katong mga viscous damper sa ubos, no? And with 3 times nga the absorber. So as we can see, nagka-decay ang iyahang vibration, no? And we've come up to our quantitative results of the TMD performance. Ako na lang i-show ang summarized na ano, no? Nara siya. So ang parameters are the following: peak acceleration, structural sway, settling time, and occupant comfort. So without TMD, ang ato ang peak acceleration has 7 to 7.9 millig. And with TMD, na-reduce siya into 4.7 to 5 millig. And structural sway is high perceptible motion if without TMD, and with TMD, reduced lateral sway. Settling time from 30 seconds to 20 seconds, and ang occupant comfort is noticeable discomfort without TMD, and with TMD is acceptable comfort range. And also for the discussion, based on the analysis and monitoring studies, the tune mass damper of Taipei 101 was very effective, reducing the response of the building during the strong wind and seismic events. And the monitoring data indicated that the peak acceleration of the building was reduced from 7 to 8 millig down to approximately 5 millig. So the reduction helped maintain the building motion with acceptable occupant comfort limits during the typhoon conditions. So the analysis also showed that the TMD absorbed a large portion of the vibration energy and dissipated it through damping. So because of this, the building stabilized faster after excitation. So without the TMD, the structure continued oscillating for a longer period, while with the TMD, the vibration decayed much more quickly. And also, overall results confirmed that the properly tuned passive control systems can significantly improve the performance, serviceability, and comfort of super tall buildings subjected to dynamic loadings. And additional information lang, the result, ang pag-monitor din nila silang full scale structural monitoring na is na sila 30 accelerometers installed across 6 different floor levels. So aside from the computer nga modeling or computer nga simulations, napod sila yung mga actual nga mga sensor nga gikabit sa building to monitor the actual dynamic performance of the building. So overall, Taipei 101 remains one of the best real-world examples of passive structural control in modern high-rise engineering. So its success demonstrated how structural dynamics, vibration control systems, and continuous structural health monitoring can be integrated to improve the safety, stability, and serviceability of the super tall buildings. So, and also these are my reference, and thank you everyone for listening.
Okay, so thank you, Engineer Urabaw, no? So we will ask question later no, after the presentation of Engineer Espinosa. And thank you very much for that presentation, Engineer Urabaw.
Thank you, sir.
So let's proceed na to Engineer Espinosa.
Wait for a while. Okay, okay, sure. Uh, Good evening, everyone. Maklaro ba?
Yeah, please
Yes, sir.
proceed.
Okay, by the way, good evening. This is my topic for the case study. It is somewhat like related to the topic of Engineer Bulahan, which is the soft soil amplification effects. No, but my topic is very general, so I research some case study relating to it na ma-apply ang soil amplification effects. No, so my case study is entitled the 1995 Kobe earthquake, Great Hanshin earthquake, a case study on subsoil amplification mechanisms and seismic responses in reclaimed urban terrains. So before I proceed, let's uh, have a question as civil engineer. No? Most of us, when we design a structural building, it seems na when an earthquake happens, murag ginapasanginlan or one of the reasons na yahitabo or ma-fail ani sa ka kuan structure once the earthquake happens kay murag yadlak siya sa design when it comes to structure mo. Pero from that, we might wonder na even if our kuan structure is enough no to go against the demand of the earthquake or the disaster, why is it that there's still some um, chances na maguba gyapon ang structure no? Maybe there are some reasons for that. Mamaya na nako topic is soil amplification effects no kay based on that nakita or they found out that the soil or the characteristic of the soil or the property of the soil is one of the reasons why there are some cases na dili lamang kung earthquake or the magnitude of the earthquake that causes the destruction of the structure no. uh, Next.